Okay, thank you for joining TechTuesday. I'm reminding you this is not legal advice. I'm just talking about concepts. And remember, the session is being recorded and will probably be published on YouTube. So don't talk about anything in particular. My goal is not to go in depth, but to spark some conversation. And if anybody also wants to do a TechTuesday, please let me know. The format, reminder, I'm going to talk about a technology, 5 minutes. I'm going to talk about problems or solutions specific to IP in that technology. Then we will have 10 minutes input from you, the participants. And that is actually the important part. Okay, I assume that people have heard the word NiTinol. NiTinol is a wonder material. You can see here, you take a paper clip, you can deform it a lot. Now, if you look really closely in this picture, you'll see the paper clip is underwater. So what happened is they poured hot water into this spoon. And NiTinol is a material which, when you heat it up, it can remember where it was before. That's called shape memory, and go back to its old shape. Now, NiTinol has many uses, but some of the most interesting ones are inside the body. For example, I'm showing here a picture from a patent about a stent. And what you see here is called a plan view. Basically, you take a piece of NiTinol, you cut it according to these lines, and then when you deliver it in the body, it expands. So, NiTinol is a biocompatible material, even though it's made out of nickel, and some people have a bad nickel allergy. If you seal it properly, because it's nickel and titanium forms a titanium oxide coating. It has two states, austenite and martensite. I hope I pronounce them correctly. Those are two different crystalline states of the material. And I'm oversimplifying because there's actually a third state as well. But what's important to know is the NiTinol is different, very different in the two states. In one state, it's soft, you can deform it. In the other one, it's hard and let's call it elastic. So when it's in the first state, you have what's called shape memory. If you took its original shape and you deformed it, the NiTinol doesn't forget. And when you remind it, it will pop back to the old shape. When it's in the hard state, it has what's called superelasticity. You know, a lot of materials, if you deform them more than 1 or 2%, they stop being elastically deformed and become plastically deformed. NiTinol can deform 12%, you know, depending on the type, and still return exactly back to the shape it was before. And last but not least, one of the ways of going between these two states is temperature. And you can tune the material so it changes state at body temperature. In other words, it will be in the soft state when it's in the room at 22 degrees Celsius. And when we put it in the body and it gets to 37 degrees, or maybe we add hot water and it gets to 41 degrees, it transitions to the other state. All of these, like I said, wonderful properties. It has all sorts of processes for setting the crystalline structure, and they can be quite complex. Manufacturing and welding, especially to other materials, is not easy, but it is doable. Last but not least, because the device is super elastic, it is commonly used where you have moving parts, like in heart valves. And then you have to ask yourself, how do we resist fatigue? So one of the big questions when you build something out of NiTinol is, how well will it resist fatigue? Okay, so this is just about NiTinol as a wonder material, and it is a wonder material. And most patents that talk about implants mention the possibility of using NiTinol. So it's biocompatible, it's super elastic. What more do you want? So here's my take on it. I think the most important thing about NiTinol, it's true about other mechanical products, but especially about devices made out of NiTinol, is that there's an intimate link between the material, the processing we provide, the mechanical design, and how we use it. So it's not just, I'm making a stent, but I can make the stent better if I make it out of NiTinol. If I make it out of NiTinol, I'll change the design. I'll have other limits on what processing I can use. There'll be different places I can put it in the body. So the first question you have to ask when you write a patent application is, does my patent application recognize that there's a link between the material and these other things? Often, what we get is a shopping list. When I talk about at the end, don't give a shopping list. Somebody writes a patent and says, oh, I have a connector, and it can be made out of any material, stainless steel, NiTinol, cobalt chrome. That's not good. That means you're not recognizing the connection between the material and what you can do with it. So that is most important. And it also means that when you talk about the solution space, which is a set of materials, design, processing, which you can use, it is not simple. The parts are interconnected. Let's go back to this drawing, figure 7 over here. You notice we have a bend. Now, when this thing is going to expand, this bend will be deformed. The amount of deformation you're allowed to have depends on the material, in this case, NiTinol, and on the processing, which says how much deformation you can have before it fails. So what do I think you need to have in the spec? Number one, you have to talk about enablement. Enablement means, can you make it? It doesn't mean, can you make it medical grade with high reliability? Unless, of course, you claim that. So it could be that you're describing a product which doesn't have high reliability, but is still enabled and therefore covered by a claim. When somebody knows how to make it more reliable, hopefully they'll be infringing your patent. Description. I'm talking here mainly about things that are often ignored when, I read a lot of patents that talk about NiTinol. What actual material are you using? There are a lot of different types of NiTinol, just like there are a lot of different types of plastic. What treatment or processing did you do to the NiTinol? And therefore, what transition temperature does it have? And what is the width of the transition? There's some hysteresis involved. When you have an implant that has high stress or high strain, like that rounded section I just showed you on the stent, you have to give the details, especially you have to talk about size and angles, because that's the difference between what you can do in stainless steel and what you can do in NiTinol. You have different states of the device before you implant it, let's say in a delivery system or in a loading system, after you deliver it into the body or while you're delivering it, and when it's actually being used. I mentioned the example of a heart valve. The part of the heart valve which moves, you want to make sure that it has the desired pliability state. Now, like any patent application, you don't want to describe just one design, you want to describe a range of designs. And I'm just reminding you again, the range of designs has to relate to the material properties. If you have a material property, you should describe a design that makes use of it, and vice versa. And I'm emphasizing the variants you're describing are going to be different from stainless steel. If they're not, you didn't do it right. Of course, all of this is provided by the client. We just need to remind them that just because he has one design doesn't mean we want to be limited to that. So, a few things to consider, and here I'm going to talk about design around. So we wrote a patent, we described the new stent design, and a lot of patents like that. You have to ask yourself, will a new shape memory or super elastic material come into being? Maybe one which is less limited by problems of annealing, fatigue, stress strain, or whatever. The answer is usually yes, it will come into being. And then the question will be, did you describe designs which are able to make use of these new properties? Now, before you ask, the end of the slide, can you see it coming? At least in medical, the answer is yes, we can see it coming. Why? It takes time from the minute somebody discovers a new material and publishes it in, I don't know, Nature Materials, until when it's approved for use inside the body. So you know that these different materials exist, they're on their way, people are working on biocompatibility, discovering the correct way of processing. They should be considered in your patent now. On the other hand, sometimes designers use NiTinol as a shortcut. Instead of making a smart design, they use a smart material, and then they can use a design which is not so good, but good enough. But the competitor might put the work in, and using plain elastic materials like stainless steel, reach the same outcome just by having a smarter design. So just because we're writing a patent about this clever NiTinol stent, we should still be asking ourselves, if we wanted to get the same properties, is it possible to do it with stainless steel or cobalt chrome, but using a different design? Now, what if you're writing a patent that's not about NiTinol? Okay, we're using a steel clip. So automatically we have to ask, what will happen if somebody comes along and discovers a way to use shape memory materials? You know, a shape memory might be too elastic, and we have to have a hard implant, a stiff implant. But if somebody used shape memory, what would happen? Would it be better? Okay, so one last point. Try to imagine the day before shape memory alloys were known. And imagine you're writing a patent about a stent made out of stainless steel. And really, this is what we do every day when we write patents. So the question is, when you were writing that patent, what assumptions would you have explored so that when this new material comes around, you're covered? So if we take the example of stents, right now, let's say the best material has failure at elongation of, I don't know, let's say 12%. Can you assume that nobody will develop a material within the next 20 years which has an elongation of 20%? That's an assumption you're making. So either the client has to say, I'm not worried about that assumption, or you have to say, well, how can we describe a design that makes use of greater elongation? Okay, this is what I had to say. Okay, I took a technology, I gave some thoughts about how it affects when we write a patent application. And now I would love to hear from you, reminding you we're using the improv format. There's no point in telling me I'm wrong. Instead, say interesting things from your experience or tricks or whatever. And we have 10 minutes.